Let's go ahead and talk about finding the average value of a function. And it turns out that the average value of an integrable function f on the closed interval from a to b, and we do use this little f bar notation, the average value, is equal to 1 over b minus a, the length of the interval, times the integral from a to b of f of x dx. So this is going to be our formula for finding the average value of a function. So where does that come from? Before we get into this example of applying that average value, let's talk about where it comes from. So let's suppose that we have a continuous function. I'm going to shrink this down just a smidge. So let's suppose we have a continuous function like I've drawn here, y equals f of x on the closed interval from a to b. Now, if we wanted to calculate what the average value is, and I drew this, and we could kind of eyeball it and say, the average value of this is probably somewhere in here, right? If we think about that, if we want to think in terms of area, it's almost like we could draw this in and we can sort of see the area, and if we were to take this piece of area and kind of settle it in, I might have drawn that a little bit low. Maybe it's a little bit higher. Maybe it's more like right in here would be the average value f bar. If we can kind of think about, taking the area and sort of settling it in, that's one way to think of the average value. But if we just think about like what would be the average function value on that interval, it's going to lie somewhere, between the high point and the low point, and it's going to be the average. Well, how do we calculate the average of a set of numbers? Well, we add up all the numbers and we divide. So if we had 50 numbers, we would add up all 50 numbers and divide by the number of numbers. So we would divide by 50. So how are we going to do that in terms of what we've been doing with Riemann sums? Well, what we're going to do is we're going to say, well, let's just split this up into n subintervals. So let's split the interval from a to b into n subintervals of length delta x equals b minus a over n. And then on each subinterval, so as we go along, we've got x1, x2, x3. On each of those subintervals, let's go ahead and pick a tag x sub k star on each subinterval, and we will use that to calculate what the function value is on the subinterval. And so then we could add up all of those function values. So to find an estimate for the average value of the function from a to b, what we could do, and it will be an estimate, so I'll use my approximation symbols. What we could do is we could add up f of x1 star plus f of x2 star, whatever that tag is. We've talked a lot about Riemann sums, so we could go right-hand endpoint, left-hand endpoint, midpoint, but some tag on there. We'll use that to calculate the function value on that interval all the way out to x sub n star, and since we're adding up n of them, if we wanted the average, we'll divide by n. But I want you to take note right here that our n could be written as b minus a over delta x. So I could actually replace this n right here with b minus a over delta x. And so this average value we could actually write as f of x1 star plus f of x2, all those function values on each subinterval, all over b minus a divided by delta x. But when we take b minus a divided by delta x, that's the same as saying b minus a. It's just flipping. Let's multiply by the reciprocal and write our delta x up here. And then let's go ahead and pull that 1 over b minus a, that's a constant, to the front. And this piece here is a summation, so let's write it as such. The sum from k equals 1 to n of f of x sub I, f of x sub k, so I used k, keep wanting to use I, times delta x. And that's an approximation for the average value of our function f of x on the interval from a to b. But what do I do if I want to make it exact, right? Because this gets closer and closer to the exact value, the exact average value, as we let n get bigger and bigger and bigger. Well, we can make n go all the way to infinity by adding in a limit. So notice that we can go ahead and say the limit as n goes to infinity of 1 over b minus a times the sum from k equals 1 to n of f of x sub k star times delta x. And this, by the way, is just a constant, so I'm actually going to smooth that out in front of the limit. So I'm going to write that as 1 over b minus x. That's just the length of the interval, 1 divided by the length of the interval, so that's a constant. Let's move that all the way outside of the limit. Now, notice that this is a Riemann sum. And a Riemann sum is a definite integral. So we can actually say, and this is no longer an approximation now that I've added in the limit, this is actually the average value. F bar is what we will call the average value, and we can say equals. This is the average value of f of x on the interval from a to b. We have just made it exact by throwing in that limit as n goes to infinity. And this is a Riemann sum, so we can finish this out by saying that this is exactly equal to, I'm actually going to come up here where I have a little more space. We can come over here and say that f bar is exactly equal to 1 over b minus a, the Riemann sum, is equal to the definite integral from a to b of f of x dx. And we have just shown that the average value of a function using, let's see if we can get it all on the screen here. There we go. Using what we know about averages, right? We add up, if we want to find the average of a set of numbers, we add up all those numbers and divide by the number of numbers we're adding, number of quantities we're adding up. And that's exactly what we're doing here. We're just saying let's start with an approximation of the average value by just taking n subintervals, but then we let n go to infinity. And as we take n to infinity, we see that Riemann sum, which is a definite integral, and we can get this formula. And so that's where the formula that I had projected at the beginning came from. So let's go ahead and go back to. So let's put this average value of a function into practice. So where would we use this? Well, we would use it anytime we want to look at a continuous function on a closed interval and determine where would be that average value. What's the average of the function across that whole interval? So here we've got an example. Suppose that h of x, for height, is equal to this function, 45x cubed minus 520x squared plus 1000x plus 4200. And that measures the elevation above sea level of a hiking trail where x is the horizontal distance in miles along the trail. Determine the average elevation on the interval from 0 to 8. So for 0 to 8 miles, let's determine what that average elevation is, where we have a function that's measuring elevation above sea level. So we can see from 0 on the graph, I went ahead and grabbed this graph out of Desmos, so we can see from 0 to 8, just drew over the 8, from 0 to 8, we can focus in from 0 to 8, and we can see that this elevation is starting a little above 4,000, it's going up. The hiking trail, it looks like there's a gain in elevation, and then it drops down and then starts to go back up. So where would be the average, right? If we want the average of this hiking trail, where would be the average? Well, I mean, just eyeballing it, I don't know, maybe kind of in there somewhere. maybe even a little bit higher. The average somewhere in there would probably be about the average of the elevations across that interval from 0 to 8. So let's figure out what is that number, what is that average for this? And we're going to do that just by applying the average value of a function formula. So if we want the average value, so I'm going to use h bar, since my function is h, it's going to be equal to 1 over the length that we're looking at. We're going from 0 to 8. So 1 over 8 minus 0, so we're looking at, that's the length of the interval that we're looking at this function on, times the integral from 0 to 8 of that function. So that's 45 x cubed minus 520x squared plus 1000x plus 4200 dx. And that's how we're going to find the average value. And so this becomes a definite integral problem. So we're going to get 1/8 and then go ahead and find the integral of this, which is going to be 45 over 4 x to the 4th minus 520 over 3 x cubed plus 500 x squared plus 4200 x, evaluated from 0 to 8. So then we'll apply our fundamental theorem of calculus. So this is 1/8 times 45 fourths times 8 to the 4th minus 520 over 3 times 8 cubed plus 500 times 8 squared plus 4200 times 8 minus, and when we plug in 0 into this polynomial, we're going to get 0. Okay? Minus 0. And h bar is then going to be equal to, when I plug that into the calculator, and hopefully you guys are okay if I just go ahead and give us the answer here, which is 8,600, plugging it into my trusty calculator, 8,600 over 3, which of course is equal to 2,866 and 2/3 or 0.6 repeating, or approximately, well, since the 6 repeats here, it's approximately 2,867 feet. And I think, you know, for purposes of the context here, let's go ahead and go with the approximation as our answer to, we'll go to a whole number. We're on a hiking trail. I don't think we need to worry about fractions of a foot on the average. And so if we come back to where we were looking at, so I don't know, we're a little bit below 3,000. And if we come back to sort of the intuitive, the visual here in the graph, and we were talking about, you know, where is that? So it was 28, right about there. We were pretty close. Okay, it was 2867 was the average value h bar of this function, and that looks about right. And you know, in some ways, you know, you can sort of think about like there's this, you know, this area is sort of like settling in and filling in that, you know, that area below. This particular graph that we're looking at has some nice, what appears to be some symmetry there, and we can sort of see that happening, kind of that essentially, when we're thinking areas, you know, that area kind of coming in and filling in that area, settling in almost, you know, to make it this solid rectangle of average function. Okay, let's finish off this video by talking about the mean value theorem for integrals. So we've been talking about the average value of a function on an interval, a continuous function on an interval. So what the mean value theorem says is simply this: if we have this continuous function and you know, we could find its average value, then there has to exist a point C in the open interval from A to B such that f of C is actually equal to that average value. And so f of C is equal to the average value. So there has to be at least one C where that value of the function is actually equal to that average value. So how do we do that? Well, let's take a look at an example. We'll see how that's going to work. We'll see if we can keep that up there. So if we have f of x equals e to the x on the closed interval from 0 to 2, let's find all the points at which the function is equal to its average value on that interval. So we'll find all of them if there's more than one. but there'll be at least one by this mean value theorem because we know that e to the x is a continuous function. So we can find its average value, and then we can figure out what point C in between 0 and 2 generates or gives us that average value, is exactly equal to that average value. So start by finding f bar. That's just going to be 1 over 2 minus 0 times the integral from 0 to 2 of e to the x dx. And so that's just 1/2 integral from 0 to 2 e to the x dx. And so f bar is actually 1/2, and the integral of e to the x, that's one of the easiest ones, is e to the x from 0 to 2. So we get 1/2 times e squared minus e to the 0. And so my average value of the function from 0 to 2 of e to the x is 1/2 e squared minus 1. Okay, so now we want to find all the points where the function is actually equal to that average value. So now we want to find all points C in the open interval from 0 to 2 where f of C is actually equal to f bar, which in our case, of course, is 1/2 e squared minus 1. All right, well, let's see if I can keep it on the screen there, but give myself some space. So f of C is e to the c, so when is e to the c equal to 1/2 e squared minus 1? So let's find that c value. We could have left that as x if we wanted to, but I'll use c since that's how the theorem is written. So, well, how would I solve for c? Remember that this is just a constant. This is just a number over here. We never approximated it. I guess we could. Let's actually do that real quick. 1/2 e squared minus 1 is, just so we have a reference here, that's approximately 3.19. Okay. So remember, that's just a number. So if we wanted to find c, anytime we want to solve an exponential, we'll go ahead and just take the log of both sides. So c is equal to the natural log of 1/2 e squared minus 1. And since we're here approximating, let's go ahead and approximate that as well. Okay, so that c value is approximately 1.16. That's good enough. We'll just go 2 decimals. So it's approximately 1.16. So that is our answer. That is clearly in the interval between, remember that is between 0 and 2. And that point would give us this average value. So if we plug c back into f, we would get that average value. And if we want to see the value here, if we want to see a visual and see those values on a graph in Desmos, we can go ahead and do that. So notice what I have here is I wrote our function, so that's what we're seeing graphed in red. So in Desmos, I did the graph of our function here in red, which is just e to the x. And of course, I restricted the domain because we were only looking at it from 0 to 2. So we were only looking at that from 0 to 2. So in Desmos, you can see in red the graph of e to the x. And then I graphed in blue here, I went ahead and graphed our average value. So that is just a horizontal line, the average value. This was f bar. And this is f of x. Okay, so we can see f of x and we can see the average value. And you can see the approximation there, 3.19 was that average value. And what you can see, I think Desmos will even give me that point. What you can see is right there where I've got that ordered pair, you can see, let's see if I can hover and show you. You can see right there that 1.16 that we solved using the mean value theorem for integrals. You can see that x value that we found, 1.16. And so that's the point on the x-axis. It's not going to let me draw on that, but that's the point on the x-axis where the function you know, the value of that C value, that X value, is actually equal to the average value. So you can see it happening there on the graph. And that is our mean value theorem for integrals. And that wraps up this section, working with integrals.